Hello folks, today we are going over the segmentation tree. I'll be kind of giving it a little context by having a problem here. This is from LeetCode, so you can look at the source here. I'll put the link in the description, of course. I'll be covering this in Python specifically, but because I'll be going through it, hopefully it'll be clear enough that you can implement this in any other object-oriented way that you want. Given an integer array nums, find the sum of the elements between indices I and j, such that I is always less than or equal to j, and this is inclusive. The update function, or method in this case, will be given an I and a value. The function modifies the number at index I to be that new value. There's also this concept of querying. So for example, if we have an array like this, 1, 3, 5, then we can find the sum of the range between 0 and 2, so 0 being the first index all the way up to the last one here. That should total 9. We can then update this data structure and select this position 1 and make it a 2. And then if we try querying that range again, we'll get an 8. And so that's what we'll be covering. But first, I kind of want to go into how this thing makes sense at all, and then implementing the code after that. So let's assume that we have the nums array as 3, 4, 10, 2, and 7. And the way that we're going to look at any range is by aggregating to get the sum. You can also aggregate to get the min within that range, or the max within that range, or any other kind of aggregation that you can think of. So how this thing is going to work is we're going to be dealing with a tree structure. And there are some efficiencies that tree structures allow us to kind of eke out, and that's the benefit of using a segmentation tree for looking at a aggregate of a range within a array or list. And so we're going to start with the root node. So the root node is going to have basically everything inside of it. So if we look at the root node, it's going to encompass the entire range from 0 index to index 4 in this case, and it's going to be the sum of all of that. So that'll be 26. What then happens is that we will split it just like a kind of binary tree in this way. We're going to split the range in half and separate those out. So the root node gets split into 2 children nodes, and what we're basically going to do is we're going to take the range that it represents and split that in half as well. Now we have an odd number of elements, so it really is up to you how you want to split that left or right. It really doesn't matter too much as long as you're consistent. So here in this case I'll just put the extra on the left, but again, it doesn't really matter too much. And what we see here is that now we have the range between 0 and 2 on the left, which is 3, 4, 10, which is total 17. And then on the right, we have 3 and a 4, the last 2, and that's equal 9. And basically, we'll just keep doing this. We're going to break down the tree structure until we get to the individual elements represented by the actual literal number 3, 4, 10, and just each one by itself. Okay, and so what we'll have here now is we can see that the tree gets broken down to this point that we now have the individual elements being represented on the very bottom nodes. And so we see now that we basically have, now we can kind of look at this from the bottom up in a way. And the thing that I want to impress upon you is that this data structure, because it's a tree, there's some well-defined properties of this kind of structure that we can take advantage of. The first thing to note here is that the length of our original array is 5. So let's keep that in mind. So the fact that it has a length 5 actually helps determine how large our tree is. You can imagine that having a length 10 means that we need more nodes to kind of deal with that. So this number ties into how large we need our structure to be. And that's going to be important because what we're going to end up doing is building out the infrastructure first and then filling it in basically. So let's think about how many nodes we're going to need. The first thing to realize is that the nodes depends on the actual height of the tree. So we need to kind of tie in the height with this length, which we can do because it's this binary tree. So how do we do that? I want you to think for a second about how the binary properties work, and to realize that anytime we kind of traverse, we're basically reducing things we're either doubling or reducing it by 2. And if we're going the other way, we're going backwards. We're going from this number at the bottom to 1. We're actually, each step, we're taking the log of that previous number. So in the end, what we're looking for is like log of 5. And I'm going to show you what that looks like. So we can see that if we take the a log with a base 2 of 5, we get about 2.3. And let's tie that into what we see here. We have 2 tiers of nodes with like one little bit of extra. And that's what like the 0.3 is basically saying. Like it covers 2 for sure, but then there's a little extra. So what we want to do when we're creating our structure, we want to make sure we have enough room to fill everything in. So we're going to actually ceiling this, and we're going to say that the height is the ceiling of log 2 for 5. Okay, so we are now able to establish the height of this tree given the length of the original input list. If this was 100, that height is going to be different, but it all depends on the length of the list, of course. And we always do the ceiling because we want to make sure we have enough room to fill in everything. Even if there's going to be some empty, you have to imagine there are going to be like empty nodes here that are under these, but that's okay because, it's a little extra space. It's not that big of a deal. The thing we definitely want to know is how many nodes we're going to need. What we're going to be implementing is this tree structure in an array form. It's going to basically be a list that represents this tree. And to do that, we need to know how many nodes, how large that list is going to need to be. So we can use this height to basically determine that. So if we imagine that we filled in those empty nodes, how many nodes do we have on the actual very bottom of the tree? Here, that's a total of 8. So we have 8 nodes at the bottom. This is super helpful because of the binary nature of this tree structure. We know that everything on top of it is basically like this. It's just a doubling effect. So if you look on top of it, you have 4, and on top of that is 2, then 3. So everything on top of the 8 is actually 7. And you'll find this to be a very regular pattern. If you take the nodes at a certain level, everything on top of it is basically twice that, but minus 1. So we know how many nodes we are going to be dealing with based on the height. The height is 3 here. How do we get 8? It's just 2 to the third power. It's just a binary thing where you can just do math basically. So let's see what that looks like in the math. So if we actually calculate the number of nodes that we need to allot space for, it would be 2 to the height, 2 to the power of the height, which is 3 in this case. We multiply that by 2, and then we just subtract 1. So in this situation, it would be 15. We would create and allocate in memory space for 15 elements, which are going to represent our nodes. Now, in this case, we're not actually using all of them. We have a bunch here at the bottom, these 6 that are not totally being used. But again, not such a big deal because those are just being allocated for the potential that they could be used. Okay, so now that you can get a sense of what the structure is going to look like, I want to show you how it will be implemented as a list instead of an actual like tree structure with node objects. That's not what we're going to be using. This is much more convenient, and this is typically how segmentation trees are also done. Let's try and simplify this tree structure into just a regular list. That's a little easier to handle. So imagine that we just have a regular list or array, and I want to start with the root. That's usually where you start. So let's start there. I would put the number 26 because that's where our root is, 26 here. Something I forgot to mention here is that you'll notice that each parent is the summation of the children. That's the point. That's the convenience. So when we do our query searching, we're going to be using this convenience to our benefit because we can quickly see the value or the sum of a range by like looking at the parents, which already have the pre-computed values there. So if we start with 26 as our root node, I could put the next 2 children right under it as 17, 9. And then I'm just basically copying the rows left to right, top to bottom. So I'm going to now go 7, 10, 10, 3, 4, and maybe none. And, it'll just be a bunch of empty spaces until you get a total of 15, but I'm not really worried about those. So this list is how we can think about this tree structure. So let's see how that even makes any kind of sense. So I'll just zoom in here. And I want to show you here that these numbers have an index. You can actually get from the parent to the child index in a very reliable way. What you can do is, from this, so these are the 2 children, right? This is the left child and this is the right child. So this left child can actually just be calculated based on the index of the parent. If you're looking for the left child, you just take the current parent index times 2 plus 1. And for the right, it's basically the same thing. It's just going to be times 2 plus 2. And that's all we got to do. Let's see another example here. So if we apply the math, we see that we'll take the left is equal to the current index, which is 1, the parent, times 2 plus 1, that's 3. 1 times 2 plus 2, that's 4. And that's how you can get those children. If we look at the 9, its children are the 2 times 2 plus 1, that's 5. So you go to index 5, that's the left child. And 2 times 2 plus 2 is 6, that's the right child. So this consistency is actually pretty well known. So if you ever really see tree structures that get implemented, sometimes you'll see them just as a list and using this kind of math. So this is not too unfamiliar for if you're dealing with trees. Let's dig into actually implementing this thing in code. The first thing I'm going to do is I'm going to write some tests. So here I'm going to write some tests. I'm going to just copy some of this here, like nums. So what I'll be doing eventually is creating a class that's like a segmentation tree class. So the way I want to do that is to instantiate it. So I will, even though I don't have the code right now, I will implement it like that. And I want to initialize it with a input list. Okay, and then we should be able to assert that if I do st.query on 0 and 2, that this is supposed to equal 9. Then if I do st.update 1, 2, and then do my query again, this should equal 8. So that's one thing to note here. I think I want to also implement my example as well. Okay, so I've just made a secondary test here, which is using the example from before that I was writing out, where I create another segmentation tree, query it on this, and get a update here and here. All right, so this is the tests are now done. If I try running these tests, let's see what happens. Probably not a whole lot. Yeah, so as expected, there's no segmentation tree defined, and so that's what I should definitely do. So let's start writing some code here. So let's build a class, segmentation tree. I will initialize it with some input list. What do I want to do with that? So there are many ways of implementing this. I'm not saying that the way I'm about to do it is like the tried and true only way of doing it. Of course not. You can modify this many different ways. So I just hope that the way I explain it is well enough that you can actually implement it and modify it in your own ways. So one of the things I like to do here is to take this input list and just do a quick copy on it, just so I have an internal thing to work with. So I'm going to actually do self.input list, and that's going to equal this input list, and I'm just going to copy it. So this is the copy of input list. So I keep that internal. I kind of like the idea of not having all my code in the init. That's not where it belongs. There should be a separation of responsibility. So I definitely want to create some kind of like init tree functionality, and I have it call another method that's internal. Anytime I put an underscore in front of something, that means that I do not want the end user to be accessing it. That's just the implied nomenclature, the syntax. So let's do that. And it doesn't take any arguments. It has this internal storage of the input list. So what do I do? What am I trying to do here? The thing I'm trying to do here is to create segmentation tree infrastructure. That's the point. And that's what we were doing before when we did all those calculations. So first I'm going to need to get the length of list. We're going to need to calculate the height, calc the number of nodes. Then I will create empty seg tree list. And then I will want to actually populate that list. Or I'm going to call it propagate. Propagate this thing. Okay, so it's a lot of stuff, but it's not too hard, really. So the length of the list. All right, so let's create n equals length of self dot input tree, or input list. That's going to be that length. The height, we saw that that is going to be a log base 2. So there's going to be some things that we may want to import here just for convenience. Seal and log 2. So these are two functions we can take in from the math, which is part of the base Python. So we're not like cheating or anything. All right, so let's calculate the height. So height equals, we're going to do log 2 of n, and we were going to do the seal on top of that. And the number of nodes is very easy because it's just n nodes equals 2 times 2 to the height. And then we just minus 1 off that. So now we know the number of nodes. We can just create an internal segmentation tree list, which is going to be the representation of the tree. So I'm going to store that as seg tree list. Actually, I don't want anyone to have access to this, and I'll make it like a little bit more shorthand as well. Seg tree, I'll just call it. Equals a none to the times the number of nodes. So that's a quick way of like creating a list of n length, all filled with none in this case. Okay, so now we're going to want to propagate our tree here. Fill in segmentation tree. Separation of responsibility, I want to make sure that this function has the sole job of just taking the input list and then propagating it and filling in the parents accordingly. That's all it's going to be doing. So let's call that function propagate. Okay, what does propagate take? Well, let's consider something here. The idea here is we're going to need to keep track of two things. First, we need to notice that each node basically has two things going on with it. First, it has its own literal index within the segmentation tree. So by that I mean 0, 1, 2, or whatever. That number, that index, does not correspond with this little number I have up top on what it represents, because that node also is a representation of the range of values that it's the sum of. So in this case, like 0, 2, that represents 3, 4, and 10 all together. So the three things that we need to keep track of are the literal segmentation node index, and then we also need to keep track of the range that that node represents. In this case, like 0 to 2. So those are actually two numbers. So what we have are three things: the left and right range or interval, and then the index. So we need to keep those three things in mind when we're looking at our propagate function or method. So let's keep that in mind. So I'm going to call this self. So the three things I'm going to put in here are the like array left, which is going to be like I'm referencing to the original input list, like the index that it represents for the left and right interval. So that's array left and array right. And then the actual segmentation node index. So those three things are what we'll be using here. And the thing I'm also going to mention is that this is going to be a recursive call here. So we're going to implement this recursively. Let's see, when we call it though, we need to kind of put some stuff in here. So let's keep track of these three things. And I'm going to go very long-winded here just to make it super clear. So these values are going to be our starting point. Where do we start? At the root. So seg node index is 0. And the left is going to be 0 as well, because you're talking about the range of the input list. And then the right is going to be whatever the length is minus 1, which we already have here. So it's n minus 1. So we're going to propagate starting at the root. That's all that's basically saying. And the root is represented by 0 to 4, or the whole range basically. So that's what that is showing there. Okay, so when we're doing a recursive call, which is a very useful thing when you're dealing with trees, we need to keep track of our base cases. What we're going to be doing is we're going to be splitting the range in half to kind of get closer and closer to children that are singular children, basically, that only represent one value in the original input list. So this is something that we want to keep track of and make sure that these two don't ever go past each other. So that's one very clear base case we do not want. So let's say if array left, let's say that array right is less than array left. That's when you go past. So this is went too far. Then we want to just stop the recursive call, just return at that point, just stop everything. Another base case to consider is when, like I mentioned before, when you've basically drilled down until you got to a single node. So what that looks like is if you go down to like this node here, which only has a range of 3 to 3, basically, it's a singular value, and that represents the original value in the input array. So that's a point where we want to stop as well. So if our array left equals array right, this is when we've honed in target index, index being the original input list for index. So what do we want to do? Let's grab the value. So grab value from input list. So the value is going to be self dot input list, and we're going to use the index for that, but that's basically represent the left and the right. They're the same thing, so I'm just going to grab the right one, or the left one. So that's us grabbing it, and then we just need to assign value into segtree at correct index. What index is that? That is what this is. The seg node index is the current segmentation node index that we're looking at. And so this is self dot, what did I call it? Segtree. This thing, segtree. And the index is this seg node index. And that equals whatever value. And so that's us assigning the value. We want to make sure that we stop once we do that, because we're basically done. We don't want to do any more recursive calling. So we'll return there. Any other situation is basically a situation where you have a range of values, like 3 to 4 or 0 to 2. That's what these are parents, basically. So the leaf nodes are the ones that are like done, and we don't go further. That's like the 2, the 3, the 4 here that you don't want to move past. But the parents are the ones that are being considered at this point. So once we get past these two base cases, now we're going to be dealing with the recursive call. So what does this mean? This means that we're at a parent node, and we're going to need to split into 2, basically. And what we're going to do is we're going to take the array left and the array right and find the middle point there. And that's our first step here. So midpoint. I'm going to take my array left and array right. I'm going to add them together, and then I'm going to split them by dividing by 2. And the thing I'll note here is that this is floor division. It doesn't really matter where you put the extra value if it's an odd number, as long as you're consistent. So in this case, the floor division will work out, I think, to put the extra on the left side. But again, as long as you're consistent, it doesn't really matter too much. All right, so that is where the midpoint is. Now let's handle the left side and then the right side. Okay, so again, I'm going to be super explicit here as much as I can be. So the left side, so the seg node index, if you remember how we calculated it before, it's basically down here. It's this stuff where we take whatever the current one is times 2 plus 1. That's the left-hand side. And the right one is times the current node times 2 plus 2. So that's the thing that's what we're doing here. So we're going to take the current seg node index, which is the parent one, times 2 plus 1. And then the thing to keep track of is then also the values that we're going to put in here. What does it represent? So in the case of a parent, let me go back up here. So for like the 0, 4, that's the root. The one on the left is going to be 0. So the original left side is the same, but the thing that we change is the right-hand side, which is now going to be the midpoint that we calculated. So here, I'm going to try and not be confusing. So I'm going to say left node array left. Okay, so that's so that should be 0. So that's the same thing as the parent one. So this array left is the same thing. So that's not changing. But the left node array right, again, not trying to be confusing here, is the midpoint. Okay. And here we can actually just have the recursive call happen here. So we're going to say self.propagate. Yeah. And what are we going to put in there? We're going to put in the array left, but not that one. We're going to put in this because this is the left node array left and the left node array right. And then the left segmentation node index, the node that represents. So that's what that is, and that is the recursive call there. We're going to do the same thing for the right-hand side, basically. So let's keep in mind that I don't want to change the word right to left for everything, because this one I definitely want to keep. And we know that the right segmentation node index is not +1, but +2. Now, we're not going to be... The left side is actually the midpoint, and so again, I'm going to look back here. So like the midpoint here is going to be, well, it's not going to be 2, right? Because that was the midpoint for the left. So I need to always +1 for the right midpoint, which is this side here. So this is going to be midpoint +1, and I want to take a note here. Like this might go over, and that's part of why we have this base case here. In case the right hand side goes too far, we can just say don't worry about it. And the right node array right is just taking from the parents. Again, the 0, 4, 3, 4, the 4 is the same, right? Because it's the parents one. So I'm going to just grab that from the parent array right. That's what we have here. And then it would also do a recursive call. So the thing that changes here is this is now the right node array left and the right node array right, as well as the right seg node index. Okay, so I know that seems like a lot, and it's basically when you get to a parent, you just have a recursive call go down to the children, and eventually those children will be populated. How? Well, first, this is going to populate it, because this is where we put the actual value in the segmentation tree. The other is when the children are done, and now as the parent, we have to handle the parent. And all we're going to do here is, now that the children are taken care of, because of the recursive call, we're going to say, okay, the left val is equal to the segmentation tree, which is here. We're going to grab the left seg node index, and that's the value that is at that point. And then we're going to do the same thing for the right. The right value. So we have left value, right value. What do we do to the parent? Well, guess what? Self.seg tree. And this is the current parent node index, which is this. And we're going to go down here, and we're going to say, hey, you are now equal to the left val plus the right val. So we're handling the parent. I will note here that this is where we are defining what the aggregation is here. So aggregation equals sum. And the reason I make note of that is because you may do some other kind of aggregation that you want to change that up. And so this is where you would do that chain. All right, so I'm going to save this, and I'm just going to show you, I'm just going to comment some of this out just to show you what this looks like. st2.segtree. Just to show you what that looks like. So if I run this code, we can see 26, 17, 9. All that stuff that we saw here is the same thing that we saw before down here. Okay, so with that in mind, we basically have our segmentation tree, the internal list, set up. But what we are not doing yet is the functionality that we're looking for here, which is to query and update. So let me return these. We need to figure out this implementation of how we're going to query on the range that we're looking for. And what's interesting is we can actually use a lot of this propagate logic in the same way. So I'm actually going to just like kind of copy and paste this, because we're going to be basically doing the same thing. We're going to be searching our tree for a specific range, and just returning the value. But we need to do so with a slightly different implementation. So here I'm going to just copy and paste this. And this one is not going to be called propagate. This one is going to be called query. No underscore in front of it because I want to expose this to the users. I'm actually going to do something else here. So I think what I want is to have the user interface with this, and I want to have an internal query like helper, which is going to actually because I do need that segmentation node index when we're navigating. So I definitely want to have that. So what does this look like? This is going to be called, and what's interesting is because if I go back to what we're looking at here, we have to keep track of now two more things. The things that we're keeping track of already whenever we're navigating is the left and right index, which correspond to the original input list index, as well as the segmentation node index. Those are the three things we're still kind of juggling at when we're traversing the tree. Now we have two more things to keep in mind, which is the actual query range, which again has its own left and right. So now it's like 5 things we're keeping track of. Fortunately, those two numbers, the query left and right, are not changing, so we're just kind of like passing them around. But they should be in the signature here. So I'm going to keep this these two things different here. This is a different left and right. This is like the query left, and this is the query right. And I'm going to make sure to copy that in here for our helper. So the helper is going to have query left, query right, as well as an original array left, array right, and a segmentation node index. And actually, when we called our propagate method, we had a lot of stuff that kind of like made sense here. So I'm going to kind of copy this, because when we call that function, or method I should say, the helper method, we're going to be using basically the same thing, except we're now going to input 2 more values, which is the query left, query right. And we're going to be start searching from root node. That's all. Okay, so this is going to still be a recursive implementation, but things are going to be a little bit different in terms of our base cases. The thing to note is we definitely want to make sure that this is like definitely one base case. There's another, so this is us going too far. But I want to make sure that we're being careful here, because we're not just stopping execution. We're actually kind of like getting and trying to source all of the values and summing them all together. And so what I mean by that is when we get a parent, and let's say I'm querying a range of 0 to 3. What does that look like? So I go to the root node, and I see that the range for 0 to 3 is like, it's within the current node, but it's not completely captured. So I would need to go looking for it left and right. If I go to the left, I see the 0, 2. That range is completely within the query. So I would actually say 17 is what I'm looking for as one part. So I just say 17 plus, and I need to grab the value on the right-hand side from the recursive call from the root. So I'd go down the right, and I'd see the 3, 4. Again, it's not quite exactly what you're looking for. You go down here to the 3, and that's what you're looking for. So this thing needs to return to the parent that value, and then this needs to return that 2 up to the root. So the root is going to have a 17 and a 2 coming in from that, and that should return an actual value. We can't just halt the recursive call. We actually need to return some value. So the value we're going to return is 0, because when we add 0 to a sum, it's going to not change anything. So that's one thing to keep in mind. So that's one base case. Another is kind of like I mentioned before, where we're looking for things that are within the query range. What if the current node that you're investigating is actually outside of the query range? What do? You return 0, because it's not going to be valid. So what does that look like? Keep in mind that the query range is maybe, so the rightmost of the query range, if it is to the left of the node's left, then that means that that node is out of the range. It's too far to the right, basically. So if my query right is further to the left than my node's left, then that means I'm too far. Same thing goes on the right hand side. So that means my array right is to the left of the query left. In those both cases, we want to return that. And again, this is the case of the node is outside of query range. If you wanted to, you can group these two if statements together because they're kind of doing the same thing, but I'm just trying to be clear for everyone. Okay, so those are those two situations. There's another base case, which is what happens if your current node is completely within the range of the query. That's perfect. That's the optimization that we're looking for. So if I go back here, that's basically the situation of the 1.3 query where I don't need to go any further because this parent node has already summed up and it completely captures the summation of those values. So this is the efficiency that we're seeing here. This binary searching allows us, and the pre-computing step allows us to quickly get sums without having to traverse the entire tree and also the entire input list. So that's where this is like the power right here. So this is when if our query left is less than or equal to the node's left. So less than or equal, meaning that we're at 0, 0, it's okay. Same thing, we need to say an and here because it needs to be both of these. It needs to be true. That our node right is also less than or equal to the query right. This is saying that the current node completely within query range. And in that case, what do? Well, we just return the current value. The current node's value is exactly the thing we want to give out. So we're going to refer to it as self segtree, and we're going to use the segnode index that we're currently at. So that's another base case where we found what we need and we can just return it right away. Okay, so this array left or right doesn't really matter because the part that matters is if the node is within that, which is effectively going to be true only if you need to go all the way down to the last value. So this we don't need. What happens if we're doing this recursive call? Recursive call here means we're at a parent that is partially covering the query. And we need to split, and we need to grab the left or right and determine what the value is from those two. So basically the same thing is true. We need to get the midpoint just like we've been doing. Same logic is there. We need to have the left and right established of what range that node represents. And we're not calling propagate, right? We're going to be calling this query helper function, or method I should say. And we need to pass in the query left and right, which does not change even as we pass it into the next node as we search for that. And we're going to take the left node array, that one and that one. And we should remember that this query helper is returning a value. So what we want to do is actually capture this value. So this is our left val, which may be 0 or maybe actually a number. Either way, it's just passing up what is found. Same thing is true for our right-hand side. So I need to make sure to copy this, put that in here. So the query left, query right, that doesn't change. Right node, array left, and everything else is the same from before. And again, this one is returning a value, so we need to make sure this is our right val is equal to that. It's returning a value. And now we can handle the parent. And we don't need to do this lookup because it is already handled for us. The left and right value are already there. And I am not going to be assigning values. This is not assignment. We are returning. So we're going to return left and right. And again, this is a point where the aggregation is summation here. So again, if you abstract that aggregating function, you might want to do that here. Okay, so I believe this will allow us to now query properly. So if I run my test, this should work, and this should work, and then update should stop because we don't have an update function. So let's check this out. Let's see here. We're told another problem. We're told array right does not have an n. We don't have an n value on line 75. Let's see that. Yeah, look at that. N minus 1, right? Okay, so here's where we can maybe go back and think about where we established n, which was during the init tree call. So yeah, this thing here. So what we can do is just keep this as an internal reference, which I think is pretty easy. So self.n. Sure. And then I just need to make sure anytime I reference n, which is like here and here, that I make sure to reference that. Anywhere else? I think the only other place was here during the query. Okay, so it's just an internalized n to refer to the length of the input list, which I could also just reference as the length of the input list. It's a little excessive, but anyway. Okay, so if I run that now, query, oh, it doesn't equal 9 is what it's saying. Okay, let me like print. What is that then? None? Oh, it's returning none here. Why is that? Okay, so let's check this out. This query helper is being called by the query method, but it's not actually returning a value. So we also need to make sure return the value from the query helper. That makes sense, I think. Okay, so let's try that again. Hey, there we go. So I printed 9 and segmentation tree does not have an update. Okay, that's fair. So let's go back and put that back in. Let me just take out my print statement. Okay. Yeah, so we don't have a update function. So here's the cool thing. We have conveniently set up our propagate method to pull everything from the input list. You know, it's basically what it's doing is that it's going down all the way to the bottom of the tree. Once it hits the bottom that has only a single range or value for a range, it's then pulling everything from the internal input list and just like propagating everything up to the parents. So this propagate thing is actually really convenient. All we need to do is go into our internalized input list and just update it via the index that the user is going to be familiar with. So all I really need to do here, define update. Oops. And we're given an array index, which is the original input list index, a new value. And all you would really have to do is say self.input list array index equals new value. And that's kind of it. And then you would propagate. But here's the thing. Here's the minor optimization I'm going to suggest. This is fine. And so I could just call self.propagate and be on my way. That's totally fine. Here's the optimization. If you're using a lot of updates, you don't want to keep having to propagate every single time. You may want to just update the input list until you're ready to query. And then you kick off the propagate. So that's what I'm going to suggest doing here. Again, minor optimization. So I would want to keep an internal state reference to whether or not the state of that segmentation tree is propagated or not. Can we trust the parents, basically? So I'm going to go all the way up to the top. And during my init, I'm going to say self dot is an internal thing. So is propagated equals true. Because at that point, when we do init tree, that kicks off the propagation, so it will have been propagated. So that's why that is okay to say true. But when we do our update, we'll say propagate is false. And then so we're not calling propagate yet. So we can do like a million updates. All it's doing is changing this internal index, which is constant time. So it's really efficient. And then the next time we do our query, basically our query, we're going to say, okay, check if self is propagated. Or I should say not, if it's not propagated. Then we just kick off propagate. And then it propagates, and then it will do the query. So that's a nice quick convenience there. Another thing I will note here is that you may not, again, minor efficiency here, where it's possible that the value isn't changing. So you could kind of like check the old value, and then say if old value is not equal to new value, then do all this. Otherwise, you don't need to do anything because it's not changing anything. Again, minor efficiency. This is what is considered a lazy update. Lazy because we're not propagating until we are truly ready to do so. Okay, so let's see if this will pass our test now. Propagate missing 3 arguments. Oh, you're not wrong about that. Okay, so if I recall correctly, propagate does require some arguments. Actually, it requires these arguments. So what I'm going to do is I'm going to just like move these up. So this is like only propagate if internal, and I need to propagate. I need to feed in all these values that are supposed to be fed in when we call propagate, and then I can start searching from then on. Okay, so these values need to be established either way, so that's why I can like put them at the top. Okay, fair enough. Let's go again. Ooh, all right. Propagate takes 4 positional. 6 are given. What's going on with that? Line 110. Let's see here. Oh, look at that. Oh, I mistakenly forgot to update this when I changed it. So for the query helper, I need to make sure that the recursive call is properly recursing on itself and not calling some other method, which is what I was doing before. Okay, so let's try again. Hey, it passed the test. And we now, folks, have a working segmentation tree. Of course, I'll be leaving the code in a gist, so you can always check that out. I mentioned before that this aggregation here is something you can abstract. So you can imagine that there is maybe an internal thing with that when you instantiate it. You can maybe say there's some aggregation function, and I'm going to store that internally. Self.ag function equals this thing. And then this is what you would call then when you do any aggregation. So that's like when I did this here, this plus. I don't want to handle that. That should not be my responsibility to keep that logic in the code. I should let the user define how they want to aggregate 2 values, and I pass that in. And the user is now the one who determines whether they want to sum or not. So I leave that as a challenge to you to actually figure that one out. All right, folks, so I hope that was helpful. If this is something you find useful and you enjoy these kinds of videos, please make sure to like, subscribe, and do all the good things. And I will see you next time. Take care.